So in the previous two lectures, I showed you how to compute or how to derive simple preconditioners for simple problems, and then more complicated preconditioners like multigrid for simple problems. And now I would like to try to generalize this a little bit to more complex problems. So of course the world does not consist only of the Laplace equation, even though we mathematicians like to pretend this a lot of times. But the world consists of fluid flow that is described by the Navier-Stokes equations, or of coupled problems where you have let's say temperature conduction, and that is coupled to some elastic deformation of the medium, and then maybe some chemical reactions, and so on and so forth. So the real world, of course, looks a lot more complicated. And so the question is, if you have one of these more complicated problems, how do you approach this? How do you precondition for these sort of systems? And so what I would like to do in this lecture is that I show you a few approaches that, let's say, historically have not worked out so well, but that give you a little bit of an idea of why we need to work on this, and that give you the background to understand why we can approach this in a different way in the next lecture that I'm going to talk about. So this lecture is going to be about simple preconditioners for complex problems. And to define maybe what complex problems are, so in particular I want to talk about non-scalar problems and non-trivial problems. So non-scalar means, well, in deal.II lingo, vector value problems. That means you have solution variables that are not scalar but vector valued in possibly of multiple types. So let's say in Stokes, for example, you would have velocities and pressures. So here's a few examples of non-trivial problems. So one of the simpler ones is the Stokes equation. The Stokes equation says, well, the velocity, the Laplacian of the velocity is equal to some right-hand side minus the gradient of the pressure. So the pressure is a driving force for the velocity. But then I also have that the divergence of u equals 0. That means that the medium is incompressible. And if I wanted to generalize this to higher velocities, then the correct model would be the Navier-Stokes equation. So the Navier-Stokes equations have an additional term here, u dot gradient u. Then, of course, you have, for example, coupled problems like thermoelasticity. So the thermoelasticity would be, let's say you have a temperature variable, and the temperature diffuses in a medium. There is a heat source Q, for example. The temperature diffuses, and then you have coupled to this an elasticity equation where the source term for the elasticity is the gradient of the temperature. So it would be, for example, that you would have a medium that is clamped at the boundary, for example, but then if you have that it is hot in some parts and colder in other parts, it wants to expand in the hot parts, and it will have to be compressed in the colder parts, for example, to keep the overall volume. So you will have this sort of interplay between the temperature gradients and the elastic deformation. So that would be a coupled problem where you have two different kinds of velocity, two different kinds of variables, the temperature and the displacements here. Another kind of coupled problem would be the biharmonic equation, which we often write like this. So we introduce a variable v that equals Laplace u, or minus Laplace u, and then minus Laplace v equals the right-hand side f. Now, if I take v equals minus Laplace u from this first equation, I can insert this into the second equation, and you get back the biharmonic equation. Of course, the advantage of this particular formulation is that that I only need second derivatives of my variables. So these are all examples of the kind of problems that I have in mind when I want to talk about constructing preconditioners for non-trivial problems. And I can make this, of course, much more complicated. So in particular, in this coupled physics problem, I can think of any number of other complicating factors. I could make this time dependent. I could add, let's say, nonlinear material behavior, and so on and so forth. So I can add other variables that would play a role in there. But you get the idea that I often end up with problems that don't look like the Laplace equation. So if I look at these sort of equations, then after a discretization, like we did, for example, in step 20, you will find that the structure of the operator that I applied to the solution induces a block-structured matrix. So in the Stokes equation, I end up with a matrix that looks like this. So there's a Laplace operator up here acting on the velocity. There's a gradient, and it's transposed to divergence. And there's nothing that acts on the pressure in the second equation. If you have the Navier-Stokes equation, you also have the advection term here, for example. If you go back to the thermoelasticity problem, I have a Laplace operator acting on the temperature. I have the elasticity operator acting on the displacement here. And I have an operator that applies to the temperature that shows up in the elasticity equation. And similarly for the biharmonic equation. So what I get is that if I re-enumerate the degrees of freedom in such a way that, for example, I get first all of the velocities and then all of the pressures, then my matrix typically has a structure like this. So I often end up with these matrices that we call block-structured. So ultimately, and I will come back to this more in the next lecture, I will want to use this block structure very heavily to construct good preconditioners. That is something that I think in the early days of constructing preconditioners for these sort of problems, we did not quite realize that the block structure can be exploited to great benefit. Rather, what people tried to do in the beginning was they tried to generalize things like the Jacobi method or the SOR method or SSOR. And I would like to walk you through, let's say, the ideas that are behind this generalization approach. So if you look at Stokes, I'm going to take Stokes as the prototypical example, but it applies to many of the other problems as well. If you look at the Stokes equation, the matrix looks like this. So Laplace, gradient, gradient transpose, or divergence, and 0 here. And you could think, well, all right, well, let's do just what we did for the Laplace equation. We're just going to apply the Jacobi or the Gauss-Seidel method to it. But the answer is that cannot work, because in all of these methods, I needed to divide by the diagonal entries of the matrix. Right? So the Jacobi preconditioner, for example, just takes the diagonal of this entire matrix here. It's going to take the diagonal and multiply in each iteration by the inverse of the diagonal. Well, I've got a 0 block here, so there are 0 elements on the diagonal. I cannot invert the diagonal. It's just not going to work. So immediately, all of these methods are out of the picture if you have any of these kind of matrices that have a 0 block on the diagonal. And that's actually a fairly common case, that you have a 0 block on the diagonal. So the question is, what do you do in a case like this? Now, the first idea is we try to generalize this somehow. And so let us try to reinterpret a little bit what Jacobi actually does. So the Jacobi method, as I said, takes the preconditioner, p to the minus 1, equals to the inverse of the diagonal. And essentially what it does, if you think of the Laplace equation, for example, for the Laplace equation we have that per node, for example, in the case of Q1 elements per vertex, there is 1 degree of freedom. Okay, so a node is the place where a degree of freedom is defined. For Q1, that's the vertices. For Q2, that's also the vertices and also the midpoints of the edges and faces and cells. Okay, so we have scalar elements, and there is 1 degree of freedom per node. And then essentially what the Jacobi preconditioner does is it walks over all of the nodes from 1 through n and updates the value of the solution at this point based on just the residual that I can compute there, and I get the residual at this point based on just the local neighborhood. So we call these sort of solvers, or these sort of iterations, point solvers, because they look at 1 point at a time. So 1 point equals 1 node, but historically we called them point solvers. So they go to 1 node, they compute the residual based on the neighboring nodes, they update the value here, and then they move on to the next node or next point. That is what Jacobi does, and Gauss-Seidel, SOR, and SSOR can be reinterpreted in exactly the same kind of way. They just compute the residual differently. So the Jacobi method computes the residual at every node based on the neighboring degrees of freedom, taking the old values of the, let's say, from the previous iteration. Whereas Gauss-Seidel, SOR, and SSOR compute the residual based on the neighbors, taking either the old value from xk minus 1, if it has not been updated, or they take the new value from xk plus 1 if one of the neighboring nodes has already been updated in this iteration. But ultimately, they all work the same. We can all consider them as point solvers. They walk through all of the nodes of our mesh, and they update them one at a time. So with this sort of interpretation, we can come up with a generalization of Jacobi that we would want to apply for the Stokes equation. So let's assume for a moment that we use the Q1 element. So Q1 for the velocities and Q1 for the pressure. And I'm going to ignore the fact that this is not a stable discretization for the Stokes equation. I just want to explain to you the process of coming up with preconditioners for these sort of things. So don't try this at home. Don't try to use a Q1 element for the Stokes equation. It's not going to work. But it gives you an idea of how we come up with these preconditioners. So if we use a Q1 element for the discretization, then I have, for example, in this mesh with 9 vertices or 9 nodes, at every one of these nodes, I will have an x velocity and a y velocity and a pressure. And let me enumerate these degrees of freedom in the following way. 0, 1, 2, so the x velocity at this node has is degree of freedom 0, the y velocity is degree of freedom 1, and the pressure is degree of freedom 2. And then I'm going to move on here, and I'm going to say the x velocity is degree of freedom 3, the y velocity is degree of freedom 4, the pressure is 5, and so on and so forth. That is one possible enumeration. There are, of course, many others. I could, for example, have enumerated first all of the x velocities, and then all of the y velocities, and then all of the pressures. But let's say I have chosen this particular enumeration. Then my matrix is going to look like this. So the matrix is going to be a big matrix of size, what did we have here? We had 27 degrees of freedom in total, so it's a 27 by 27 matrix. But I can think of it as being composed of 9 by 9 blocks, each of which are 3 by 3. Namely, these are all of the degrees of freedom that are defined on the first vertex, and then these are all the ones that are defined on the second vertex, and so on and so forth. So that is also the structure of my solution vector, of course, u1, v1, p1, and then u2, v2, p2. Okay? So I can consider my 27 by 27 matrix as something that is composed of 9 by 9, 3 by 3 systems. And 9, of course, corresponds to the total number of vertices. I have 9 vertices here. So then let me define the following equivalent of the Jacobi preconditioner. Namely, instead of just taking the diagonal of this matrix, I'm going to take, well, a block diagonal. So this D is, I take this term loosely, it's a block diagonal. Namely, I'm going to take all of the 3 by 3 blocks that are sitting on the diagonal, okay, and I'm going to take this to the minus 1. And based on this structure of this matrix, because all of these other entries here I have set to 0, inverting this matrix that I have here is not particularly difficult. It just requires me to invert 9 3 by 3 systems. That is something that I can do very easily, right? So if I do this, I get the equivalent of a block Jacobi preconditioner. And of course, I can generalize this, for example, to something like a block Gauss-Seidel or block SSOR by also taking, for example, the lower left terms over here, in which case I just consider this whole thing as a block triangular system. Okay? So there is a matrix or a preconditioner that is cheap to compute and cheap to apply. All I ever need to do is I need to invert 3 by 3 matrices. And so I can still call this a point solver, right? Because what I'm going to do is I'm going to walk through every point, through every node or vertex of my mesh, and I'm going to update it based on the surrounding nodes. And updating a node in that case means that I'm not just updating a single degree of freedom, but I'm actually updating all 3 of the degrees of freedom that are defined at this particular vertex. So that's why we call these things point solvers. So the problem, of course, happens when I actually look at the Stokes equation in reality, and I find that Q1 is not a viable alternative. I cannot solve with Q1 unless I stabilize this matrix. Rather, what I need to do is I need to use a stable combination of elements, and here is one, a Q1 element, for example. So in that case, I have the vertices of my cells. This is where I have the x, y, and p velocity defined, but then also at the midpoints of the edges and at the center of the cell, I also have additional velocity degrees of freedom, but no pressure degrees of freedom. Okay, so in a case like this, it is not immediately clear anymore what it actually means to define a point solver, because the points are not all the same. In a point solver, I would want to do the same operation at every point, or at every node, but here I have certain things happening at the vertices, and then I have other things happening at these nodes here where there's no pressure that's defined. So I can't define point systems. I can't come up with the equivalent of a point of a block Jacobi, for example. And the solution to this sort of problem was proposed by Bangerth in 1986. Who said essentially what you want to do is the pressures are somehow special. The pressures are the ones that give us trouble because they have this zero block on the diagonal. So what I should do is I should define a local problem for each pressure degree of freedom. And then I should do something like in the spirit of Jacobi or SSOR, where I'm going to walk through all of the pressure degrees of freedom, and I'm going to update the pressure plus all of the velocities that are coupled with it, and do this one pressure node by pressure node at a time. So this is what we typically call the Bangerth preconditioner. We walk over all of the nodes where we have a pressure defined, and then we're going to solve local problems by looking at the pressure plus all of the velocities that couple with it. And so in the case of the Q1 element, it's relatively easy to see that, for example, for this pressure node here in the center, you end up with, well, the velocities, every velocity that you see here is actually coupled with this particular pressure node. So you get systems that are fairly large, certainly much larger than 3 by 3. But ultimately, the Bangerth method is not terrible. It certainly works. It is a proper generalization of Jacobi, and you can do the same thing as for SSOR. And in particular, you can generalize this to all sorts of other saddle point problems where you have a zero block on the diagonal. So that's the first idea. The experience work is that it sort of works. It doesn't work overly well. It shares the same kind of problems as Jacobi and SSOR. In particular, information propagates only from one node to the next in every iteration. And so I think, in summary, the Bangerth kind of preconditioners have fallen a little bit out of favor since the late 1990s. So when we started deal.II in the late 90s, we still implemented the Bangerth preconditioner. I think today we probably wouldn't do it anymore because I think we have better ways of doing this. But I want to introduce you to these sort of concepts because that is the proper generalization of something like a Jacobi preconditioner. So The second idea that you could have is you could just apply an ILU or an incomplete Cholesky decomposition to this whole matrix. And the experience with this is that actually just works fine. That certainly works better than something like Vanka or any other generalization that you could have from these stationary defect correction iterations. The problem is that typically these couple problems lead to very large problems. So if you have something like a Stokes system with a Q2, Q1 element, then you end up not just with, for example, 5 or 7 or 9 entries per row, but you actually have very quickly get to 100, or in 3D to several hundred entries per row. And as a consequence, computing something like an LU factorization, even an incomplete LU factorization, becomes a very expensive and very memory expensive process too. So ILU and IC are certainly viable methods for couple problems, but you relatively quickly run into limitations of how well that the problem just becomes too big for this. And so that is the fundamental limitation to this. Okay, so the third possibility that you would have is that you try to generalize multigrid. So I showed you in the previous lecture how multigrid works, for example, for the Laplace equation. And you could think that the very same thing should apply for couple problems as well as for scalar problems. In particular, multigrid has this excellent property that it propagates information through the entire mesh in every iteration, right? Now, if you think, for example, of Stokes certainly has an elliptic character. It is a couple problem where information or where the solution everywhere is affected by the right-hand side everywhere. So it is an elliptic kind of problem. So why not use multigrid on the entire system, on the coupled system? Now, it turns out that the experience is that it's not quite that easy. And the fundamental problem is that when you have multigrid, well, multigrid consists of two components. It has the smoothing component, and then it has the grid transfer from fine to coarse and from coarse to fine. The problem with couple problems is the smoother. If you want to solve something like the Stokes equations with multigrid, you need to have smoothers that preserve the fundamental property of the solution of the Stokes equation, namely that it's divergence-free. And it's very difficult to come up with smoothers that preserve this. In particular, you remember when we talked about multigrid, what we use for the smoother is oftentimes something like, well, an SSOR step. Now, you might want to think of what is the smoother for Stokes. Well, we would need to generalize SSOR, for example, by something like, well, a block point smoother or something like a Vanka. Well, these sort of things are very difficult to write in such a way that they preserve the divergence freeness. And as a consequence, it's very difficult to come up with multigrid methods for couple problems that work on the entire couple problem all at once. So people tried in the 90s and in the early 2000s to come up with multigrid methods for couple problems. And it did not really seem to work out so well. So just like the Vanka preconditioner, direct multigrid for coupled problems has a little bit fallen out of favor. I'm going to show you how we get around this in the next lecture, where we want to apply something like multigrid for coupled problems, but we're not going to apply it for the whole problem. We're going to apply it to individual pieces. So multigrid itself for coupled problems is not all that successful as well. So in essence, if I sum this up, finding good preconditioners, finding good simple preconditioners, things that we know how to do based on the discussions that we had in the last two lectures, for coupled problems turns out to actually be surprisingly difficult. The things like Jacobi and SSOR do not work, because they need to divide by the diagonal elements, which might be 0. That things like Vanka do work, but not very well, and that multigrid could at least work in theory, but is actually very difficult to make work in practice. So the takeaway message of this is that none of these three actually are used very much in practice. What is used is, for example, ILUs, or incomplete Cholesky decompositions. But then ultimately, we moved away from this, let's say, idea of using simple preconditioners for complex problems. What we needed to do is think out of the box of how to make this work. And I'm going to talk about this in the next lecture, of how we use the block structure of these systems, and how we can use the block structure to come up with much more elegant and much better preconditioners for these block structures problems.